Hi, I'm Jeff Nolan. Welcome to Charged Up, unveiling the story behind the battery boom. I'm here with Majid Abbasi to talk about all things batteries today. So we're here today to talk about batteries, and few technology trends in our time have elicited as much excitement, optimism, disagreement as batteries. And they've come a long way from the days of the D-cell and your portable radio. It'd be easy to say that battery electric vehicles have been a tipping point in the development of battery technology, but the truth is that this stuff has been heavily invested in over decades, and what we're seeing now are the fruits of those investments. So today we find our global manufacturing capacity for batteries has eclipsed really all predictions, and more is to come. Not only do we have a massive increase in the manufacturing capacity, we also have new battery chemistries, we have recycling, form factors, new materials, and a drive to solid state. And we're going to cover all of that in our episode today. And with us is Majid Abbasi, Global Battery Industry Manager at Coherent, the perfect expert to talk about these trends. So welcome. Thank you for joining us today. And I'm going to jump in and just hit you with the first question about capacity. So what is the global capacity as measured in kilowatt hours today for global manufacturing?
First of all, thanks for having me. It's an honor to be here. The answer is less than 1 terawatt hour of annual production. 1 terawatt hour, which is 1,000 gigawatt hours of production.
Wow. But it's still a big number, though, considering where it was even just 3 years ago.
Yeah.
Okay. So what's coming online in the next 12 to 24 months?
So the low forecasts predict about 3 terawatt hour of EV battery production by the year 2030. If you include energy storage and electronics, that will be about 6 terawatt hour by 2030. The more optimistic forecast would go up to 9 terawatt hour of production. So that's about 9-fold increase from today.
So, and I've seen those same numbers. Is that achievable with current manufacturing processes? Any of those cases, optimistic, base, or medium?
Yes, conservative forecast. Yes, as we speak, there are many gigafactories being constructed. Many of them would come on board in the next 24 months. So if the rate continues to be like this, I would say yes.
Okay, anode and cathode materials. Do we have that supply chain for 9 terawatt hours?
That we don't at the moment. There is a significant investment, and there's a campaign going on to mine more, process more. The main bottleneck would be processing those materials. And then also there are different chemistries that are being developed, not just lithium, other chemistries also. So we should be able to see a significant increase in production of raw materials to meet that target.
Excellent. Okay, so I want to build a battery factory.
Okay.
What do I need to budget for it?
A lot of different things. Starting from R&D phase, you come up with a chemistry, with a design, with a cell design, and then you pilot produce that, validate it, and then plan for a gigafactory. Gigafactories are massive structures with a lot of different equipments and processes that go into them. As an example, to produce 10 gigawatt hour of battery production annually, you might need about 100 acres of land for that gigafactory and about $1 billion investment. That does not even include the material processing side. So you just bring in the material to that gigafactory and make cells and modules and packs.
Okay.
That is the scale of investment we're talking about.
Okay. So walk me through what one of these factories looks like. So let's assume that I'm getting all of my materials processed and they're coming in one end of the factory, right? What happens from the receiving dock to the shipping dock?
Right. So just a very broad overview, materials would be mixed. Right now the industry is producing lithium-ion batteries, which is a slurry-based coating material. Active materials coated on metallic foils. On the anode side, you would have, let's say, graphite or that the graphite silicon, that family
Yeah.
of materials coated on copper foil. And then on the cathode side, you would have like LFP compound or NMC compound on aluminum foil coated, and then would go through a drying process to drive out the solvent. And then after that, you would have a foil that is dried, and you would slit it and cut it into narrower stripes. Then after that would be, let's say, shape cutting. You would cut the shape of the foil or based on your cell format, and then stacking, formation. There would be welding to connect the metallic foils
Yeah.
to carry the current and charge and discharge practically. Then after that, you would have enclosure welding to seal in many cases. So that's typically cell, and once the cell is made, you would have charging, discharging, testing. Well, before that, there is electrolyte injection, and then once the cells are made, then would move to the module and pack assembly, which you would have like multiple cells in a configuration, and typically laser welded to make packs and modules.
So all of this has to happen like incredibly fast to achieve the economics that are necessary for that kind of investment.
Correct, especially the cell production.
And the yield has to be there too. You can't have you can't have quality issues.
Yes, so we are like modern gigafactories are talking about parts per ppm level failure, which is parts per million. Like very few parts in a million cell is allowed to fail.
Wow. Yeah. It's like semiconductors basically.
Yep.
Yeah. Okay, so all right. So I might have to put off my battery factory plans for a little bit, but we'll see. Maybe interest rates will come down. Yeah. Who knows? All right. So lasers. We sell lasers and equipment for this industry.
Mm-hmm.
How are lasers used in this process?
Lasers are actually used greatly, and the application of lasers is expanding. Majority of application would be on welding, foil to tab welding, enclosure welding, bus bar welding, module welding, but also there are emerging applications on foil cutting with lasers, with also on slurry material drying with lasers, to some extent laser texturing of either bare foil or active material, laser cleaning before welding, or let's say after electrolyte filling. So there is a variety of applications that are either in mass production or being developed for mass production or pure R&D.
So in that foil, in the drying process, are you drying out water or is it a chemical, a solvent?
It depends on the chemistry. Some chemistries use water as solvent, like LFP, for example, or graphite anode. The solvent could be water, and then you drive out that water by drying. Some other compounds like NMC uses an organic and somewhat toxic solvent.
Yeah.
So it depends on the chemistry.
But in each case, the goal is to drive out that liquid without disrupting the composition of the base material.
Correct, and maintaining the microstructure of the active material.
Yeah.
So currently, that is done by convection oven drying, which is typically very long furnace. In a gigafactory, it could be as long as 100 meters. Utilizing laser either as hybrid or pure laser to dry the foil can save a lot of footprint, and also long-term operational cost would be
Energy efficient.
Yeah, exactly.
Yeah.
Especially where the energy is expensive.
Yeah. Yeah. And so when you end up with the coating, what's the thickness of the coating typically?
Again, varies with the chemistry, but typically, so both double-sided coatings are typically less than 200 micrometer thickness. But again, with anode and the cathode, and each chemistry would be different.
Okay. So, competing methods for drying. Okay, but what about for the welding and cutting? Competing methods there.
So-
Mechanical, I guess. Would be
Conventional processes, like you said, are mechanical. Ultrasonic welding is a great technology. It's actually metallurgic is a very good technology. The issue with ultrasonic welding is that every time you have to use a tool to contact a metallic part and weld it, that tool would experience wear.
Yeah.
And we are talking about a gigafactory with a cycle time of less than a second to produce hundreds of thousands and millions of cells per day, per week. So the lifetime of the tool plays a big factor. Ultrasonic welding is the main mechanical process used currently. Electrical resistance welding and other processes are used somewhat also, but mostly in smaller scale.
Yeah.
Lasers have shown very promising solution to tackle that high speed, high volume mass production when it comes to welding.
Do you also run the risk of deformations in materials if you're using a mechanical method and touching it with a tool? If it's not precisely calibrated, which then creates a quality problem.
Yes. So the concept behind ultrasonic welding is to actually generate that deformation, and by that plastic deformation, you combine, you mix them like different foils and metals,
right,
and then create that joint. But if that, let's say, plastic deformation energy is excessive, then it runs into like micro cracking and tear, and on the other side, you would have under welding, which means that there's not enough energy to create the bonding needed. So that again goes back most to the tool and out of calibration. So when the tools actually wear, the calibration goes off. Becomes off too. So,
All right. So we talk a lot about cylindrical batteries, but now let's go talk about like pouch batteries, where you've got potentially a big stack of foils. That must be considerably harder to manage when if you have 40 foils stacked up on top of each other.
Precisely. So ultrasonic welding actually is more applicable to pouch and prismatic cells. For the cylindrical ones, the skinny ones don't use a lot of welding, but the bigger cylindrical cells, which is gaining popularity, they need some kind of welding to connect the foils to either the tab or the can,
right,
or the cap.
Right.
So yes, when increasing the number of foils actually limits what process you can use to weld. Typically 60, 80 foils are the max number of foils you can use ultrasonic welding for.
Yeah. Okay.
Reliably in mass production.
So Coherent, years back, we introduced the ARM laser, the adjustable ring mode laser, and that's been pretty much bread and butter. It creates a preheat zone and a post-heat zone, and that allows for optimal heat absorption with no adverse effects. Why has that method proved to be particularly desirable for battery manufacturers?
So one thing that ARM laser and almost any other dual beam laser does is to enhance the keyhole stability. So,
what's a keyhole?
So keyhole is a tunnel formed in the molten metal, and so when you shine the laser to, let's say, a metal, that metal is transformed to molten state, and then the energy is so intense that creates practically vaporizes that liquid metal, and there is gas that exits
through the keyhole.
So that creates a long well or tunnel in the weld pool. That tunnel could be unstable because there's violent reactions. There's gas, there's liquid that trying to interact with each other. So that keyhole stability is critical, because every time this keyhole collapses, there could be a macro cavity left and solidified. So you would end up with porosity.
And that would be bad.
Exactly. And also spatter. Battery,
the
the spatter means small droplets of molten metal that can solidify and contaminate the cell and cause short circuiting. So that's another factor. Every time you stabilize that keyhole, it's a bonus. It's an advantage. ARM does a good job with data stability. It reduces the spatter. It maintains good depth of penetration, and then plus what we offer, what Coherent offer, is independent control of core and the ring, which means you can turn one off, keep the other one on, preheat, post-heat, so modulate or manipulate the way the weld cools or heats, and that brings in like advantages to prevent or to minimize weld defects.
So, and that is achievable with a laser because we can shape the beam. We can't do that with other methods of welding.
Yes.
So you create a preheat zone on the front end of the ring. You got a post-heat zone on the back end of the ring. You got the keyhole in the center. Mm-hmm. The idea is you're creating stability around the keyhole that allows for the escape of the gases and the reformation of the base material in a predictable way. And it creates a really just clean, spatter-free, high-quality weld.
Correct. It would not be a spatter-free, but definitely,
clean. Let's call it clean.
Yeah.
Okay. All right, good. That's a good explanation. Thanks. Okay. So, well, speaking of lithium, what is it about lithium in all of the elements that makes it particularly desirable for batteries?
Its chemical and physical properties. It's a small atom. It can diffuse very quickly and fast. The diffusion rate is high, so it can charge and discharge, practically migrate to anode and cathode very effectively.
Yeah. Are there alternatives to lithium that have similar properties?
There are. Like recently, you probably have heard in the news that sodium-ion batteries became commercial.
Yeah.
There are also aluminum-based chemistries. There's magnesium-based chemistries.
Sulfur.
Sulfur also, but sulfur typically couples with lithium.
Selenium too, I think, would be in the same category as sulfur, right? Group 6.
Yeah. On the small size atoms, I would say sodium, lithium, aluminum, and to some extent maybe magnesium would be alternative.
So if you wanted to switch your chemistries, do your manufacturing processes effectively stay the same in the machinery, the tooling you've used, invested in?
To some extent, yes. For example, the cell manufacturing. If eventually whatever chemistry you use, eventually you have to have it in a cell format, either cylindrical, pouch, prismatic, or smaller coins, for example.
Yeah.
So processes to make them to that format are comparable.
Okay. Yeah. So high nickel cathodes, silicon anodes, interconnects. There's a lot of money going into this stuff, and it kind of feels a little bit like the Wild West, like it's just getting sprayed. Money's getting sprayed everywhere. So is that sustainable, or are we going to see the industry settle on a handful of base chemistries, not because they offer a significant competitive advantage or disadvantage, but because they're good enough and they're hedging against future? Because if you can change the chemistry, right, you've got an incentive to say, okay, I'm going to get started with this now, and if something better comes along, I'll switch.
Right. We've seen that to some extent. For example, we've seen battery chemistry on the cathode side to kind of narrow down to NMC compounds and LFP compounds for the lithium-ion batteries. There's a range of, let's say, NMC and LFP stoichiometries.
Yeah.
Right? These are the main two families. On the anode side, graphite, and these days silicon, an alloy of silicon and graphite. And then next you'll see probably some kind of a solid state battery chemistry, lithium metal, sodium metal. So yes, while there's a range of chemistries, only a handful of them would go to, let's say, mass production because of obviously resources, because of processing, and most importantly, reliability and how those chemistries can become a reliable battery.
Okay.
With the required lifetime, because if you are making a battery for EV, it has to have at least, let's say, a minimum 1,000 cycle lifetime. So some of those chemistries, as of now, may not be able to reach that.
Yeah, because the average age of a car is 12 years.
Yeah.
Yeah. Okay. So battery breakthroughs. Well, actually, I'm going to ask this question two ways. So, let me say, um, I'm making battery. I got my battery factory back online. Okay, I'm going. I'm
Good.
going for it.
Yep, I'm happy
All right.
for you.
So, I want to make batteries. Do I want to have batteries I want to have batteries that are high performance, that are low cost, and I can produce a lot of them, right?
Okay.
But the truth is, you're unlikely to hit all three of those points. So if I'm building a battery factory today for production in the next 2 to 3 years, what's the one metric that I need to be focused on?
That's a difficult question to ask. To answer. I would like to go with the classic statement of safety first.
Yeah.
Whatever battery you make, whatever cost, price point, it has to be safe. Especially once the battery is out in the open, very difficult to track it. Very difficult to make sure it
'cause
stays
there's
in
thousands of them in
optimum.
these
Yeah,
packs.
exactly.
Yeah.
So safety, I would say.
Okay, so define safety. What when you say safety, what do you mean?
So there are different safety standards. Battery manufacturers have different standards. Safety referring to not catching fire, reliably charging and discharging without short-circuiting and thermal events.
Yeah.
In case of an impact, let's say a car gets into an accident, that accident wouldn't lead the battery to catch fire and risk the passengers, let's say, safety. In addition to that, the fumes, smokes, or let's say residues produced as a result of, let's say, damage to a battery or fire, those could be very toxic. So
recyclability then becomes the ability to recycle a battery actually is a safety factor. In a lot of ways.
Long term, once the
Yeah.
battery reaches its end of life, where there's almost no use to it, then that recyclability becomes a big factor. There's a wave of batteries that would emerge that need to be recycled.
Yeah.
Right now, we are mostly in the production phase. We're producing a lot of batteries, but recycling would eventually catch up.
So a lot of people talk about, there's the recycling. So you break down the battery into its component parts and recover the stuff that's valuable or dangerous and discard the rest. And then there's the reuse.
Yep.
I'm going to repurpose,
Right.
But it seems pretty impractical to repurpose batteries at large scale, considering, when you get them, there's going to be different states and conditions they're going to be in.
That's why there are policies that hopefully would go to effect, and that's called battery passport or battery
I've heard
pedigree
about
stuff.
that. Yeah.
So the purpose is that you keep track of where the battery originates, how it is maintained, serviced, and what's the status.
Yeah.
And then that would help greatly to assess what should be done with that battery at the end of its life.
So you can grade it.
You can grade it.
This is an A grade. I'm going to reuse
exactly.
this one.
If it's a good grade and let's say it's kept 80% of its capacity, it's a good use for energy storage.
Yeah.
If it's not and it's not reliable, just recycling to recover the raw materials.
All right, so that's a good segue actually to the regulatory question. So, it seems self-evident given the incentives, government incentives that are going to battery manufacturing, that fiscal and regulatory policies are greatly impacting where these factories are being built.
Mm-hmm.
Are there other factors to consider, like you just mentioned, battery passport?
Yep. That's a factor. Government regulation and incentives, the state governments, state regulations and incentives play a big role. Like some countries have considered battery manufacturing as a growth engine, or electrification in general as growth engine.
Energy independence as a security policy
exactly.
too. Yeah.
So those play a big factor. Then Yeah, these are the factors I can think of at
Yeah.
the moment. So
Okay. All right, so let's switch gears and talk about other markets. So we talk a lot about cars.
Mhm.
We did talk about grid storage a little bit. What about like appliances, devices of all consumer devices, home technology? I mean, do affordable, I'm not going to say cheap, I'm going to say
Okay.
affordable, reliable, high capacity batteries change the way that product designers approach product design? If you don't have to plug something in, are you going to rethink that product?
I think so. Like that cordlessness
Yeah.
helps redesign a lot of old, let's say, appliances or electronics. Um, and to looking at the market, electronics and appliances have seen a steady and good growth annually. Um, I mean, like the battery for
Yeah.
these like electronics.
Yeah.
So, yeah, I would say it does. It does help with coming up with innovative designs that use batteries to make the product more appealing and also more convenient to use.
Yeah. It's just amazing when the most mundane products have been transformed. Like we needed to get some like little night lights for the bathrooms in our house, and got on Amazon and I bought these little battery power. They got a little little button cell in them, and they're rechargeable and they just stick on the wall anywhere you want them. It's so amazing because I mean these things were like $10 for a 2-pack, right? It wasn't a premium product, but yet this was a simple, ordinary commodity product that was completely redesigned because of a battery.
Yep.
I think we could probably see this scaling up to even large appliances in the home. If I didn't have to plug my refrigerator in, where would I want it?
The perfect examples that I always give are cordless vacuum cleaners and
Yeah.
also cordless drills.
Cordless tools.
Oh, yeah.
We're building a new house, and I can tell you, all the contractors and subcontractors, everything is cordless. Nobody plugs anything in anymore.
Very
That is
useful,
wild.
very convenient.
Yeah. Okay, so now the subject that I deliberately left this one to the latter part is solid state because everybody talks about solid state. So first
Okay.
of all, let's talk about it from the standpoint of like, how does solid state batteries work?
So the main difference with the lithium-ion battery, which is the current generation, is the lack of liquid electrolyte. So,
Okay.
so in the solid-state battery, you would, let's say, for example, you would have lithium metal in the metallic form that would migrate to the cathode side. So lithium metal is typically anode, and then the media that this lithium in the atomic form travels through would be typically a ceramic type electrolyte or separator.
Okay.
So there's a term called old solid state battery, ASSB, that applies to a configuration with with no liquid or flammable, let's say, medium.
Okay.
Yeah.
So basically, they're like all the other batteries we talked about, except you just removed the liquid from it and made them more stable.
Yes.
And so when I think about solid state batteries, my first thought is, well, they're like a capacitor. I'm going to charge them up with a bunch of with energy. It's going to just sit there until I need it, and then it'll draw it down, and I can do that an infinite amount of times. It's basically like that. Just got some different materials in it compared to what you would find in a capacitor in an electrical system.
Right, and there's a range of chemistries. Like, for example, you would have lithium oxygen batteries. You would have lithium sulfur batteries. They're different compounds.
But you still need the same basic raw materials.
But the principles are the same.
Yeah. Okay.
So,
Obstacles. What are the obstacles here?
when it comes to lithium solid-state batteries, lithium in the metallic form is a very energy dense, let's say, material.
Yeah.
So safety becomes important, extremely important. That because of the high energy and the reactivity of lithium metal, and also the lifetime. So cycle and recycle. Number of times you can cycle and recycle it. There's a phenomenon called lithium dendrite formation. So there's tiny little needles that actually get formed during this charge and discharge cycle. Um, there are approaches to minimize that. So that's one challenge. There's a lot of metallurgical challenges when it comes to lithium metal, and then there's a manufacturability and producibility. So once you deal with lithium metal foil, um, mechanical cutting would be very difficult because lithium is like cheese, very like soft.
Yeah.
Every time you have a blade, there would a very thin edge would be left
Yeah.
at the edges. So laser, for example, could be a solution to cut the foils, but then you have to consider the safety to make sure there's no reaction. So should be done in a dry room because lithium metal is very reactive to with humidity.
So you have to control control the environment.
So controlled environment. So I would say the main challenge would be technological challenges like related to lithium, and then the producibility and manufacturability would be also.
So really, it's the process challenges that we faced with lithium-ion batteries. Just all over again. It sounds like it's actually surmountable, though. I mean, it's like you just got to keep working the process to refine it to get it to the point where you can do it over and over and over again, really fast, with very few quality errors.
Yes,
quality issues.
Absolutely.
All right. Okay. Cost per kilowatt. How low can it go?
Okay, I'm not the best person to talk about this, but the number that has been around for a while has been $100 per kilowatt.
Okay.
We'll see how that would change. That has been a target for a while, but then the market has experienced large fluctuation because of the raw material costs and because of the macroeconomics, and so hopefully that $100 per kilowatt or even lower.
Okay, so let's assume we hit it. Like, what are the long-term implications of cheap energy storage? Because that's pretty low.
Yeah, I would say the accessibility and affordability. So if you think about it this way, in the U.S., for example, a lot of EV cars or high-end cars, they're pretty pricey.
Yeah,
they're luxury.
Though they definitely are.
The average consumer may not be able to afford that. But once you have cheaper batteries, or maybe even smaller cars or more practical cars, it would appeal to a lot of consumers. And the affordability is a big factor.
So let's take that $100 cost per kilowatt. Break it down. How much of that is material versus process cost?
It varies a lot, but depending on form factor and the chemistry, I would say 60% for some chemistries would be the material cost, even like sometimes 70%. And then the rest processing cost. And even within one chemistry, like for example, let's say NMC compound, you would have NMC compound that's high in cobalt, like 622, and an NMC compound that's very little in cobalt, like 811 or 9half. So the less cobalt you have, the cheaper that raw material becomes.
But the cobalt's one of the materials that can be recycled too. If we can do that at scale, that also drives down the cost, assuming the cost of recycling itself is not prohibitive.
Yep.
Which,
right. Yeah. Recycling aside, just the raw material into, let's say, cell production, that amount of cobalt in the cathode material is a big factor.
Yeah. All right. So I'm going to wind down here, but I wanted to talk about specific to BEVs. It's widely reported manufacturers are pulling back their investments. But when you look at that seems to be it's pretty much the U.S. and Europe, right? I mean, everywhere else in the world, those investments are actually increasing. True?
I've heard China had the best year when it came to EV sales last year, and I could see part of the reason being smaller cars, more affordable.
Yeah.
So
lower range.
Masses, exactly. Yeah. Masses would buy those. Yeah. There has been some slowing in investment. We've we've talked to the battery makers, and some of them have indicated that there has been explosive growth, and this year may be a year to focus on cost reduction and
To
then
digest.
exactly, and
Yeah.
then continue growing
Yeah.
like next year or the year after that. So, yeah.
But the same car manufacturers that are reporting pulling back are also rolling out new plug-in hybrids. There's still battery there, right?
Yes,
and those
absolutely.
batteries are going to get bigger, right?
Yep. So, um, an average size plug-in hybrid vehicle would use the same battery size as a small, let's say, EV car, more or less.
Okay.
So there are batteries in those as well. Um, just an opinion. Plug-in hybrid vehicles are a good transitional, let's say, solution from
Yeah.
going, let's say, from ICE to full EV. But once, let's say, the cheaper EVs, more affordable ones are available, will be interesting to see if
Yeah.
they can compete.
Yeah,
with
true.
them. Yeah.
Yeah, and they're not without complexity either. You've got two
Yeah.
different systems that are being merged together, so
Very
there is
complex
complexity. Yeah.
engineering systems. Yes.
All right, so let's. So my last question today is actually specific to your role, which is you work with a lot of battery manufacturers. So typically, what is your engagement with battery manufacturers on Coherent? Like, what do you work on with them, without revealing anything, obviously proprietary?
Sure. So yes, we talk to a lot of battery makers. We try to understand their challenges, where we can offer solutions with lasers. We engage the battery makers all the way from R&D to pilot production and mass production. We understand the mass production issues they face, and offer develop solutions and offer those solutions for battery manufacturing. So, as an example, like I already gave some examples, but let's say laser welding is an example, laser cutting, laser drying,
Yeah.
texturing, cleaning. These are laser solutions. There are also material solutions that broader Coherent corporation actually offers.
Yeah, and now materials, battery recycling technology,
Yep,
and
exactly.
everything else. So yeah, it's all kind of getting rolled in there. Complete battery supply chain solution, minus materials.
Minus
The raw- minus the
the raw materials.
Yes.
Exactly. Yep.
All right. Well, Majid, thank you for joining us today. This has been, not just a great conversation. I've learned a lot, and I've really enjoyed talking with you. And I also appreciate the work you do because you've been really passionate about this. And actually, I'm going to throw in another question, which is, of all the things to focus on in your professional life, what is it about batteries? Why batteries?
So, long story. I was in academia, then I joined industry. The industry that I joined was refinery and petrochemicals first.
Okay.
There is a lot of metallurgical issues that need to be resolved in that area. A lot of welding issues.
Yeah.
My background is welding and material science and engineering.
Yeah.
And then, fortunately, that company that I started with made a huge investment to go to batteries because they saw the future in batteries. And there are a lot of metallurgical issues, a lot of welding issues when it comes to battery mass production.
Yeah.
From there, I was introduced to the world of batteries and loved it since, and just been active in that field.
That's great. Thanks for joining us today.
I appreciate it.
Now Next and Beyond is hosted by Jeff Nolan, produced by Carly Burgall, and presented by Coherent.